Okay, so this is basically going to be like a crash course on sequential circuitry because there are a lot of nice videos out there for like combinational circuitry, but it's a little harder to find like a nice place where the basics of sequential circuitry are put together. And so basically, what I'm going to do is I'm going to build up starting from an SR latch to a we're going to go from SR latch to a D latch and finally to a D flip flop. And flip flops are really important components in general, and like they'll probably show up in a lot of problem sets and circuits, so they're really important to kind of have an understanding of. So yeah, okay. So let's start with an SR latch. So an SR latch is basically two NOR gates that are arranged like this. So here's one, here's the other, and so the output of one goes into the other, and then the output of this goes into the other. Okay. And this input is called R, and this input is called S. Okay. Now we have a truth table here. So S, R, and we're going to call this output Q, and then we're going to call this output Q naught. Okay. So yeah, so Q and Q naught. Okay, so first of all, let's just make sure that we know what the truth table is like for this. So the truth table for a NOR gate is just like so X, Y, those are the inputs and then the output. So 0, 0, 0, 1, 1, 0, 1, 1. So an OR gate outputs a 1 if any of these are 1s, right? So a NOR gate is basically an output of 0 if any of these are 1. So 0, 0, 0, it's going to output a 1 here. Okay, fine. So let's start with S is 1 and R is 0. So this is a simple case, okay? Yeah, so when S is 1, so this is 1 and R is 0. Now, since S is 1, we know that because one of these inputs are 1, the output of this is going to be 0, right? So Q naught is going to be 0. This is going to go to here, this is 0, this is 0, and this is 0, so two inputs are 0, so the output's 1. Fine. Okay, and this feeds in here. Okay, cool. So, yeah, so when S is 1 and R is 0, Q is 1 and Q naught is 0. Okay, and now if we switch these to R to be 1 and S to be 0, so if R is 1, you know that the output is going to be one of these three, so the output of this is going to be 0, so Q is going to be 0. Okay, so Q is 0, this is 0, 0, so that's 1, so Q naught is 1. Okay, cool. So 0, 1, and this is 0, and this is 1. Okay. Now if they're both 1, so yeah, in the case that they're both 1, the output of this is going to be a 0, right? And this is also going to be a 0. And so because of the truth table, this is also going to be a 0. Yeah, assuming that this is a 1. Yeah, so Q and Q naught are both going to be 0, which is kind of weird and like not ideal because Q is not supposed to equal Q naught. They're supposed to be opposites, like Q and Q naught. And we'll come to this issue in a second. Not in a second, but a little later, how to fix this. So, but generally, you're not going to want to feed 1 and 1 into here because Q should not equal Q naught. And now, here's the important one. So the reason this is so important in like sequential circuitry is because of this. So, I mean, yeah. So if you make S 0, so Q naught. So if you make S 0 and you make Q 0, what happens? So, I mean, sorry, not Q 0. You make S 0 and you make R 0. So this is 0 and this is 0. So, I mean, I don't know what the output's going to be because I don't know the input. And the output could either be a 1 or a 0. That's all that we know. So let's say fine. Let's assume that the output of this is a 1. Okay? So if this is indeed a 1, that means that the input to this one is going to be a 1. So this is going to be a 0 and a 1, which is a 0. So it's going to be a 0, and this is going to be 0, and the output is going to be a 1 as we predicted. So the actual output is a 1. Okay, fine. Now, let's say that this is a 0. And if this is, let's say, our prediction is this is 0. So this is 0, you're going to feed a 0 to here, which is going to make this, so this is 0, so this is 0, and this is 0, and so the output is 1. This is a 1. Okay, fine, that's 0. Okay, so again, the output actually is 0 as we predicted. So the reason that this is important is because let's say that let's say that Q is just shown over here, right, by itself, and the output is a 1, right? It's just just forget about all this stuff. Let's just say this Q is a 1, right? If I pass in a 0 and a 0, this Q is going to stay a 1, because remember I said, okay, well, if I predict that Q is a 1, and then you do the calculations, it actually is a 1. So if we're saying Q is a 1, and then I'm passing in these two zeros, it's going to stay 1, right? And so Q naught is 0, and Q naught is also going to stay 0, right? But if Q was 0, and Q naught was 1, and I pass in 0 and 0, they're going to stay the same. Q is going to stay 0, and Q naught is going to become 1. That's kind of cool, right? So whatever they were to begin with, they're going to stay the same when you pass in a 0. And this is a really important feature of SR latches. And the way that you can express this in a truth table is you can say when they're both 0, Q is Q previous, and Q naught is Q naught previous. Because if Q previous was 0, then Q would also be 0. So Q equals Q previous, Q naught equals Q naught previous. Okay, fine. So that's an SR latch. But the thing is, first of all, it'd be nice to actually have some way to it'd be nice to have a better way to input data into this. And it'd also be nice to not have this issue where when S and R are the same, Q is the same as Q naught, because that's a problem. So one way that we can fix this is by basically putting AND gates in front of these. Well, you'll see. So okay. So we have yeah. Okay. So this looks like a lot, but it's really not that bad. Okay, so essentially, here's what's happening. We have this SR latch, okay? And we know how this works, right? We looked at the truth table. Now, this looks a little messy, right? These two things. Because we kind of already said, we understand the basics of the SR latch, right? We know that when set is a 1, this is called set, and you're setting Q to 1. And when R is a 1, this is called reset, you're setting Q to a 0. Okay, when S and R are both 1, that's bad. You don't want that to happen because Q equals Q naught. And when they're both 0, that just means that Q equals Q previous, Q naught equals Q previous. So we know what this does, right? So we don't really have to draw this out again. We can abstract it as a chip. So rather than drawing this out, I'm going to replace this SR with a diagram that looks like this. Okay, so we just draw, and then it's it's like a slide relief. It's not as messy, it looks neater. Okay, so what is going on? So we got this clock input, and we got this D, like this data input. So first, let's notice how clock is connected to these two AND gates, right? So if clock is set to 0, it doesn't matter what this input is or what this input is. The AND gates are always going to output 0, which means that R is going to be 0 and then S is going to be 0, which means that Q is going to have the same state as it did before, and Q previous is also, like Q is going to equal Q previous and Q naught is going to equal Q naught previous. Okay, so basically, if you don't want to mess with anything, you want to keep everything the same, your clock should be 0, right? Now, if your clock changes to 1, this is where this part of the truth table comes in. So if my clock is 1, right? So this is 1, and let's say that data is 0, okay? So if data is 0 and clock is 1. So this is going to be 1, okay. Now, this D is going to be 1 because it goes through a NOT gate, so this 0 turns to a 1. So this is 1, which makes R 1, okay? And here, so then for S, clock is 1, right? And data is 0, okay? So, which makes this 0. So, okay, but we know it's SR switch though, so that's two things, right? So R is 1 and S is 0. This makes Q 0 and Q naught 1. Okay, right? So what this is basically showing is that the D is going to be copied to Q when the clock is 1. That's really important. D is output at Q when the clock is 1. And if you don't believe me, we can do this again with D equals 1. So D equals 1, okay, this is a 1, and this is a 0. So this becomes 0, this becomes 1. Look at the truth table. When R is 0 and S is 1, Q is 1, and Q naught is 0. Okay, again, D is copied to Q. Now, one important thing to notice here is that notice how S and R can never both be 1 because the D is connected to a NOT gate, right? So these two inputs are never going to be the same, the D's here, which is nice because of that. The only time that they will be the same is if they're both 0. Well, actually, no, they still won't be the same. Yeah, they're never going to be the same. Yeah, so they're not going to be the same. Okay, so that's cool, right? So basically what this means is that whenever we want to feed data into this and have it update its values, you basically just set the clock to 1. So like the clock is represented like this, like 0, 1, 0, 1, 0, like 0, 0, 1, then it goes back down to 0. And then 1, then it goes back to 0. Okay? So whenever I change the clock to a 1, whenever I change the clock to a 1, we say that this whole thing, which is called the D latch, we say it's transparent, which basically means that whatever value for D is here is going to be output by Q. And whenever the clock is a 0, we say that this thing, which is called the D latch, is opaque, which means that it's going to keep the same values. Okay? Yeah, so it's going to keep the same values, just like when these are both 0. Fine. So yeah, so this is your SR. This is your SR switch, SR latch, and this is your D latch. Okay. But the thing is that this will update all the, like, if clock is 1, this is going to keep updating whatever values you put D into. But you might want to have a little more control over when you're updating your values. And this is where a flip-flop comes in. So a D flip-flop is basically, so I'm gonna leave the truth table here, and I'm going to erase this, and I'm gonna draw a D flip-flop. Okay. So a D flip-flop looks like this. Okay, so what in the nation of tolerance is going on here? Okay, so I've got these two D latches, and this one is connected to directly to the clock, and this one is connected through a NOT gate to the clock input. And we normally call this one the master, and this one is called the slave. Yeah, so basically, here's how it works. When the clock is set to a 0, right? When the clock is set to 0, like we talked about before, if the clock is a 0, these are going to be the same as what they were before. So nothing's changing, right? The input, I don't give a crap like what D is. I really don't care. D could be anything, but the clock is 0, so it's like the whole like AND gate thing like blocks it off, right? Because like, I mean, you're feeding a 0 and whatever the data is into an AND gate. Doesn't matter what the data is, the output's going to be 0. Fine. Or the output will be a 0, which will basically cause 0, 0. And I mean, you don't need to go down. Like, the whole point is abstraction. The point is that when clock is 0, well, I mean, all I was saying was that this would be 0, so this would be 0, this would be 0, Q equals Q previous, Q not equals Q not previous. But we don't care about that right now. We've already built up from that, okay? Who cares about the SR latch? We're past that, right? I mean, so, yeah, so when clock is 0, these don't change, okay. However, if clock is 0 here, clock is going to be a 1 here, which means that this D value does matter, okay? So whatever I feed in here is going to be output. Remember, this is what we were talking about before in the D latch. When clock is a 1, whatever is input into D is output onto Q. It's not going here. It's not coming out here because this is the 0, okay? It's not going out there, but it is output on Q. But it's not going to be reflected here because this is a 0, okay? But if I want to update the value that's here, I set this to a 0, right? So this is set to a 0. So now whatever I feed into this data is going to be right here, this Q. And like, it's going to be feeding into this D, but it doesn't matter that it's feeding into D because this is going to change. But it's going to be like, it's like ready to go. It's like, oh yeah, like I'm ready to shoot out of there, but like it can't because this is a 0, okay? So let's say that I've done this and I've prepared some value here. So let's say that clock is 0, okay? And I fed in, so let's say clock is 0, which is the 1 here. Let's say that I fed in a 1 for D, okay? So this 1, because the clock is on, gets copied over to Q, and it's like right here, okay? It's right there, and it's like I'm ready to, ready to shoot out of there, but nothing's gonna happen because clock is 0 here. Now, I'm gonna change clock to a 1, okay? So clock was at 0, now it goes to 1, okay. Now, on this rising edge, this D latch, the slave, is going to copy whatever is at D is going to be copied to the output, which is Q. Okay? So the slave is going to copy whatever is at D to Q, which makes sense because when the clock is at 1, the input at D is copied to the output at Q. Just like before here when the input at D was copied to Q, same thing. And so so this is a 1, and since this is a 1, this is a 0, which means that these are just have the same values because you're not changing anything there. Because this is 0, so it's since it's a 0, it is it's opaque, which means that that's like the terminology. So it's opaque. That's what you call it when it's 0. So it's not going to copy over whatever the D. So yeah. So this is a 1. So that means that this gets copied over there, and that's the output Q. So this is important because you can control basically when you want to update your data. Because like if your clock is like 0, 1, 0, 1, every time that you hit a rising edge here, your updated data is going to be reflected here. So basically, when the clock's at a 0, you can put some data into here, this D, whatever you want to have output at the next clock edge. So like let's say right here, I'm like, okay, I'm gonna put like a 0 into the D. So I put a 0 into the D, and it's gonna be here. And then as soon as this clock edge comes up, that D is gonna be output by this Q right there. So it's cool because you can basically control when you want that to be output there. And we represent this symbol as this D flip-flop symbol can be like, I guess, abstracted as, yeah, well, it's actually, okay. So this D flip-flop symbol can be abstracted as this. And to be honest, we don't really care about the Q not, but like, whatever. So this Q, yeah, this can be abstracted as this. And this sentence is super important, okay? This is called a D flip-flop. Not that sentence, but the sentence out. I mean, that's important too, but like, okay, this sentence is called, okay, this sentence is called D flip-flop, okay? I mean, not, okay, this is called a D flip-flop, okay. Now, this is super important. When this clock is a 1, the value at D is copied to the output at Q. Okay, I'm going to say this again. When this clock is a 1, the value at D is copied to the output at Q. And the reason for this is because when this is a 1, whatever is here, which originally came from here, is going to be copied over to Q. But we abstract this entire thing as this. So all you need to worry about when you're looking at this diagram is that whenever the clock goes from a 0 to a 1 at that rising edge, the value that's here is going to be output here. And whenever it's at a 0, this value is going to be what it was before. So most of the time you're going to be working with these, but they might, like on a test, they might ask you, about how this works, or they might say, how many SR latches comprise this, or maybe even how many transistors. And I mean, you can get really far down into the NOR gates and the transistors and all that. But this is the basics of sequential circuitry. Yeah, so I hope that helped. Yeah, well, that's about it.